Hello everyone, thank you very much for watching this video. I'm Wei Zhe from Tencent AI Lab. The work I will introduce today is Leaving Cell Supervision for Cross-Domain Cloud Counting. First of all, I will introduce the task of cloud counting. Given a random image, the goal of cloud counting is to estimate the cloud quantity and the cloud location. That is, how many people in this image and where are they. Early methods rely on counting by detection technique, which assigns a bounding box for each person. Therefore, the number of bounding box equals to the number of people, and the location of bounding box is exactly the location of the cross-bounding person. This approach works well in sparse location where there are not many people. However, for dense sims with heavy occlusion, this technique generally obtains worse performance compared with counting by density map technique, which aims to regress a density map for each image. So what is cloud density map? The annotation of cloud density map is one dot on each person's head. Therefore, the number of dots equals to the number of people. We then could get the density map by Gaussian kernel. For example here, the right image is a corresponding cloud density map of the left one. Current approach in cloud counting mainly depends on the annotation of real images to achieve excellent performance. However, there are many problems with real image annotations. First of all, the annotation is extremely expensive. It takes hours for a single person to annotate such a single image. The second is that it is almost impossible for human beings to accurately annotate far-away regions where people are extremely small. Besides, exposing people pictures to annotators may also cause privacy issues. To solve these problems, many researchers propose to use synthetic data, which is much cheaper and can always get accurate annotations without any privacy issue. However, model trained with synthetic data generally works poorly on real images due to domain gap. To solve this problem, we propose a two-stage approach. In the first stage, we generate a stochastic density map, that is, maps with uncertainty attached to them, instead of more traditional deterministic one. How to achieve this? We add a mask in the network which drops different channels in different iterations. One problem for model trained with only synthetic data is that, as the model only uses synthetic data in the training stage, it overfits the synthetic domain, thus works poorly on the real domain. We address this problem by also leaving unlabeled real image in the training stage, by randomly rotate the real image upside down and add another task to predict if the unlabeled real image is upside down or not. To generate stochastic density map, we use a technique of mask samples to generate a fixed group of masks to drop channels, which obtains highly independent predictions compared with simply random dropout. In the second stage, we further use the stochastic density map to remove uncertain estimation and only keep the certain one for self-training, which means we generate reliable pseudo labels for real images and use them for model training. This brings state-of-the-art performance in public cross-domain cloud counting benchmark compared with previous work. Here are some example estimations with real images. As you can see here, even though we do not use the real annotations in model training, the model still generalizes well in real domain. In conclusion, we propose a two-stage approach to substantially increase cross-domain cloud counting performance without using ground truth real image annotations at all. Thanks for watching.